What is the time of the excursion? What's that? What's the time of your travel?
It's distance over.
Distance over velocity, right? Distance over velocity. So S as a distance traveled over velocity. But this is with constant velocity. If not constant, then you need to integrate. Right? What is ds? ds is here on the curve. This is ds, the element, length element over your curve that is unknown shape. I'm looking for y of x. Okay, so my ds, I know it. It's the square root of dx squared plus dy squared. And if y is a function of x, then I can take dx outside, and it's y plus y prime squared of x. Correct? Any question about ds? dx squared plus dy squared. Y is related to x. Y is a function of x, so dy squared is y prime, dy dx times dx. Okay, so I can substitute here for my ds now. What about the v? Oh, this is a conservative problem. So I have conservation of energy. Kinetic plus potential is constant. What is kinetic? In 1/2 mv squared. What is potential is negative mgy. I'll give you some time to write. Just bear with me for a minute. This is equal to constant. In particular, it's equal to its value at the beginning. At the beginning, v is 0 and y was 0. So this is 0. So you get your v is a square root 2gy. Let's substitute to get our time of the excursion. The problem turns out to be over x now. Is the integral. ds is here, square root 1 plus y prime squared dx over square root 2gy. Integration over x from 0 to x final, right? And I'm looking for y of x, the shape of the function y of x, that minimizes this t. If you give me y of x as a shape, and then integrate, I'm doing this integral, definite integral, I'll get a value for t. So if you do linear, you'll get some value for t. If you do exponential, you'll get some value for t. I'm looking for the shape of the function that minimizes the time of the excursion. This is the Brextochrome problem. It has to do with dynamics. And it was the beginning of calculus of variations. This is indeed a calculus of variations. Your optimization 206 will not tell you how to solve this problem. The best that you can do out of 206 is to shop your function at different instants, right? Discretize and treat the value of your function at each instant or at each x as a design value, unknown. Maybe you have n samples, you have n variables, and do it using finite dimensional optimization. But it will not tell you the mathematics behind it. This is what we're going to study next time. Okay? So, a few minutes, I'll tell you some serious applications that goes with calculus of variation. I will not exceed the 5 minutes extra that I wanted. Any questions so far? What I want you to realize is the fundamental difference between finite dimensional optimization and calculus of variations. There is a fundamental difference. Whenever you're looking for a shape of a function, do not do finite dimensional optimization. Period. Okay? Applications, infinite number of applications. You have the a wing of an airplane. So this is y, the length of the wing, the span, what we call the span, right? And we have this angle, theta of a y. Theta. There is nothing preventing me at all from changing this theta over y. This is different from the one that I started with here. And a very typical problem in airplane design to determine theta as a function of y. What is theta of y? And actually, moreover, this length of the wing, what we call it the chord, it's also a function of y. I mean, you all see wings are trapezoidals, right? theta of y and c of y, what are these functions that minimize what? Any suggestion?
Drag.
What? Drag, exactly. That minimize the induced drag in particular. This is a very, very typical problem in airplane design. And you know, probably you know the solution. If there is no twist, the optimum torque distribution is the elliptic one, and vice versa. If there is no, if it's a rectangular wing, all the lengths are the same, then the optimum twist distribution is the elliptic one. And this is the result of the unconstrained problem. If you add more constraints, it's no longer elliptic. But it's very, very typical problem in airplane design. Again, this is another airplane. And probably you can now imagine what I want to say. This is a given height, the airplane here from the takeoff, and I wanted to take off from 0 altitude to a given altitude in minimum time. If it's a fighter airplane, interceptor want to go and intercept some coming airplanes, or minimum fuel consumption if it's a commercial airplane, right? This is a calculus operations problem. This is a calculus operations problem. In my PhD, I did other things with flapping wings. There's no time to tell you about it. So see you next time. Thank you.